another section of the BJ's physics classroom. This section of the physics classroom today is going to be a continuation of the electrostatics, the series on electrostatics that we have started already. So far we have dealt with the introductory aspect of electrostatics. We have dealt with charging, methods of charging conductors. We have dealt with the gold leaf electroscope. We have dealt with the Coulomb's law. We have dealt with resultant forces. So we are going to continue today with electric field. But before we do that, I want us to look at one question, the solution, how to solve a question on the resultant forces before we move on to the electric field that we have to do. So thank you very much for being part of the show. Like I always say, if you haven't subscribed to my YouTube channel, then please do that. The channel is BJ Online. And you can also join my Facebook page, BJ Physics Classroom. Then you can also sign on to my website or log into my website, bjonline.com, where you can access physics materials that you want to use to study. So before I continue with today's work, let me, acknowledge a very good friend of mine, Mr. Asante Peter, Krobi Asante. He has been very helpful so far as this online teaching is concerned. He has been my director, watching the video and directing me, telling me what needs to be done right, what needs to be added and stuff like that. My brother, you have been a very good brother. Thank you very much. I really appreciate your effort and what you're doing for me. God richly bless you. He's also a teacher, so he knows so much about what I'm talking about. Good. So let's look at this question: resultant force on a charge. So we take an example. 3 charges are arranged 10 centimeters successively in that order in a straight line. In a straight line, that is also important. Find the resultant force on the 5 microcoulombs, the minus 4 microcoulombs, and C, the minus 3 microcoulombs. So what I'm going to do is that I am going to deal with 2 of them, and then I'll leave the last one for you. So I'm going to do A. Good. So solution. To be able to do this, we have to first sketch. To be able to do this, we have to first sketch a diagram. The diagram we are going to sketch is going to help us a lot. Usually, when the question doesn't ask you to sketch a diagram, it doesn't fetch marks. What I mean is questions of this nature, exactly, but the diagram doesn't fetch marks. But when you draw the diagram, it helps you not to get the answer wrong, exactly. A, the resultant force on the 5 microcoulombs. Resultant force on the 5 microcoulombs. A, the 5 microcoulombs. So we sketch Q1, Q2. The 3 charges are in the straight line successively. In that order means that the first one will come first, 5 microcoulombs. The next one will come first, minus 4, come next, minus 4 microcoulombs. The next one will come minus 3 microcoulombs. Then, because they are successively 10 centimeters, the distance from here to here is 10 centimeters. And the distance from here to here is 20 centimeters, because from here to here is 10. So that will be 20 centimeters. Now, I've already told you that there are so many schools of thoughts. One of them is that, like I discussed in the previous video, to look for the resultant force on Q1, which is the 5 microcoulombs, we make Q1 static. Then the rest of the other charges are going to move. So if Q1 will repel a charge, that charge will move away from Q1. If Q1 will attract a charge, that charge will move towards Q1. Between Q1, 5 microcoulombs, and Q2, minus 4 microcoulombs, there's going to be attraction because negative, positive, negative, positive. So for that matter, this charge will be attracted by this one. So it will move in this direction. Between Q1 and Q3, there is going to be attraction because this is negative and this is positive. So this charge will also move towards this direction, and we are going to have this. So F1 is this, F2 is this. Is that clear? Good. So now that we know our directions, what we do is that we try and find F1 and F2. And since they are pointing in the same direction, we add the two of them after we have found them. So we look for F1. That is the force between Q1 and Q2. That force is going to give me K, F1 is equal to K, Q1, Q2 all over D squared. So F1 is equal to 9 times 10 raised to the power 9 times Q1. 5 times 10 raised to the power negative 6. Why negative 6? Micro, negative 6. Times 4. 4 times 10 raised to the power negative 6. All over 0.1 squared. D squared. 0.1. So why 0.1? The distance between them is 10 centimeters. 10 centimeters in meters will give us 0.1. You understand? Good. So when we simplify the top, we are going to get F1 is equal to 5 times 4, 20 times 9, 180 times 10 raised to the power negative 3, this times this times this. When you deal with the standard form, all over 1 times 10 raised to the power minus 2. Why? You know, 0.1 is the same as 1 times 10 raised to the power minus 1. So when you square this, that will give me 1 times 10 raised to the power minus 2. Exactly. Good. So when this one cancels this, I'll be left with 180 times 10 raised to the power minus 1. That will give me my F1 is equal to 18 newtons. So the force between Q1 and Q2 is 18 newtons. Good. Now we look for the force between Q1 and Q3. So F2 between Q1 and Q3. That is going to give me F2 is equal to K Q1 Q3 all over D squared. F2 is equal to 9 times 10 raised to the power 9 times 5 times 10 raised to the power negative 6 times 3 times 10 raised to the power negative 6. 3, 5 times 10 raised to the power negative 6 all over 0.2 squared. Why 0.2? The distance between this one and this one is 20 centimeters. 20 centimeters in meters is 0.2. So therefore, F2 is equal to 5 times 9, 45 times 3, 135. Yes. Times 10 raised to the power minus 6. Sorry, minus 3. All over 4 times 10 raised to the power minus 2. Why? Let me explain this one. You know, 0.2 is the same as 2 times 10 raised to the power minus 1. So when you square this, 2 squared is going to give me 4. And then 10 raised to the power minus 1 is going to give me squared. When you square this one, that will give us 4 times 10 raised to the power minus 2. Good. So 4 times 10 raised to the power minus 2. Then 4 will go into this one. F2 is equal to 33.75 times 10 raised to the power minus 1. You know, when this one cancel this one, I'll get 10 raised to the power minus 1. Then this one divided by this, that will give me this one. Therefore, F2 is equal to 3.38 newtons. This is the force F2 between Q1 and Q3. So therefore, the resultant force between them, you can see that the two forces are acting in the same direction. All right. So what we do is that we add them. So the resultant force F is going to give me F1 plus F2 and that is equal to 18 plus 3.38, and that will give me 21.38 newtons. So we look at the resultant force on the minus 3 microcoulombs, all right? Resultant force on the minus 3 microcoulombs. Good. So to do this, we sketch. So this is 5 microcoulombs, Q1, Q2, minus 4 microcoulombs, and then Q3 minus 3 microcoulombs. Because we are looking for the resultant force on this one, we do this for 20 centimeters, and then we do this for 10 centimeters. You know, between this one and this one will be 10 centimeters. Between this one and this one will be 20 centimeters. Now look at this. This charge is positive. This charge is negative. So this charge is going to move towards this one because we're looking for the resultant force on this. This charge will not move. This one rather will move. So this charge will move towards this one. So between this one and this, let's call this one F2. The F2 is in this direction. But this is negative and this is negative. So between this one and this one, the force F1 is going to move this direction. Why? Because there will be a repulsion between this one and this. So this charge is going to move away. If this charge is moving away, then this force will be acting in this direction. Now you can see that the two forces, F1 and F2, are acting in opposite directions. Because they are acting in opposite direction, we will subtract the smaller force from the bigger force. So let us see how we go through this one. This is our diagram. So we look for F1. F1 between Q2 and Q3. F1 between Q2 and Q3. So that is going to give us F1 is equal to Q1, Q2 all over D squared. F1 is equal to 9 times 10 raised to the power 9 times, Q2 and Q3 times Q2. 4 times 10 raised to the power minus 6 times Q3. 3 times 10 raised to the power minus 6 all over. Remember, I'm not putting minus values here because these ones are minus. No. Micro is times 10 raised to the power minus 6. When you are solving a question, you don't bring the negative signs that are attached to this. The negative signs are only there to show you whether the force, whether the two charges will attract themselves or they will repel themselves. Good. So in the process of solving, the negative charge doesn't come in. All divided by 0.1 squared. So therefore, F1 is equal to 4, 3, 12. 12 times 12 times 9, 18, 9, 10. 108. That will give us 108 times 10 raised to the power minus 3 all over 1 times 10 raised to the power minus 2. So when we simplify this one, it will give us F1 is equal to, this one will cancel this, give me times 10 raised to the power minus 1. Then that will multiply this, that will give me 10.8 newtons. So the force between these two charges, which is pushing this one away, is 10.8 newtons. Good. So we come to F2. F2 between between Q1 and Q3. Between Q1 and Q3. So that is going to give me F2 is equal to Q1, Q3 all over D squared. So F2 is equal to K 9 times 10 raised to the power 9 times 5 times 10 raised to the power minus 5 times 10 raised to the power minus 6 times 3 times 10 raised to the power negative 6 all over 0.2 squared. So F2 is equal to, we multiply this by this by this, 9 times 5 times 3, that will give me 135 times 10 raised to the power negative 3 all over 4 times 10 raised to the power negative 2 by 4. This is 2 times 10 raised to the power minus 1. So when you square this, to give you 2 squared, 4 times 10 raised to the power minus 2. Alright? That is the reason why I got this one. So that when this one cancels this, I'll get times 10 raised to the power minus 1. This one will go into this one. F1 is equal to 33.75 times 10 raised to the power minus 1. So that simplifying this, we get F2 is equal to 3.38 newtons. You know, I'm rounding this one up to give me 3.38 newtons. So it means that the force between 5 microcoulombs and the 3 microcoulombs is this. But because the two forces are in opposite directions, we find the resultant force by subtracting. And this value is smaller than this one. So therefore, the resultant force F is equal to F1 minus F2. And that will give me 10.8 minus 3.38 newtons. So when we subtract this one from this, that will give us 7.42 newtons. This is the resultant force due to these two charges on this one. So that is basically how we deal with resultant force on charges. So what I have done is that I have found the resultant force on the 5 microcoulomb charge. I have found the resultant force on the 3 microcoulomb charge. I want you to use the principle I have used to find the resultant force on the negative 4 microcoulombs. The negative 4 microcoulombs is this. So between this one and this one, 10 centimeters. Between this one and this one, 10 centimeters. Use that, find the resultant force. The system will tell you whether you have to add or subtract. And then post the answer to me on the Facebook page and let me see who gets it. Thank you very much. Good. So we continue with today's lesson. And we start with electric field. Electric field. Now, when we say electric field, let me use this as an example. Let's say we put a spray here in this room, or an air freshener, right? Or we put an air freshener in this room. What happens is that there is going to be a region around the air freshener or the spray where anybody seated within that region will experience the fragrance, will experience the odor that is coming out from the spray or the air freshener. So the region around the spray where anybody seated within that region experiences the effect of the spray can be termed as the field around the spray. So let us bring in the charges. So when we say electric field, when we say electric field, we say it is a region around a charge where the electrostatic force due to the charge is felt. I'm taking it again. A region around a charge where the electrostatic force due to that charge is felt. That is what we call electric field. All right. So when you place a charge in an empty space, the charge exerts a force around it such that any other charge placed within that field, within that region, experience the force of that particular charge. This field, this region is what we call electric field. So that is electric field. But we look at another term we call electric lines of force. Now what happens is, within the region called electric field, there exist some imaginary lines where any test charge placed in the field moves. Let's suppose that I have a charge, negative, that has created this field around itself. There exist some imaginary lines within this field, along which any test charge placed in the field will move. So when you place a test charge here, the test charge will move to this point, and then either the test charge will move towards this or the test charge will move away from it. These imaginary lines within the electric field are what we refer to as electric lines of force. So we define electric lines of force as imaginary lines in an electric field along which a positive test charge placed in the field moves. Electric line of force. Characteristics of electric lines of force. We have 6 characteristics of electric lines of force. You know, there can be many, but we summarize them into 6 of them. 1. The lines of force are perpendicular to the surface of the charge. It means that you can't draw a charge like this and put the line of force tangential like this. No. The line of force is supposed to be perpendicular to the surface of the charge. If even it will bend, it will have to bend elsewhere, not on the surface of the charge. Exactly. That is 1. 2. The line of forces do not cross each other. So you can't draw a line of force and do them like this. No, that is abomination. They don't cross each other. 3. The lines of force are continuous and do not break. It means that you can't draw a line of force with broken lines like this. No. All right? They are continuous and do not break. 4. The lines of force repel each other. So because of the repulsion between them, it makes them exist in a state of tension. What that means is that they will appear stretched and not crooked, not zigzag. Exactly. So you can't draw a line of force and make it like this. No. Either a line of force is stretched like this or a line of force is stretched like this. Exactly. Good. So this is not. This is okay and this is okay. This is because there is a repulsive force between the adjacent line of forces. Between this line of force and this line of force, they repel each other. Between this one and the other one, they also repel each other. This is repelling this. This force is repelling this one. And this line is also repelling this. So they will be stretched. Exactly. They will not be crooked like this one. Good. That is the 4th one. Now the 5th one, the lines of force point away from the positive charge and they point towards the negative charge. So if this is negative, the lines of force will point towards it like this. If it is positive, they will point away from the charge. Number 6. Remember, they don't come in this order that I'm giving to them. Anyone can be number 1, anyone can be number 2. Number 6. So I'm bringing them out as I remember them. Exactly. Number 6. The lines of force are concentrated at a point where the electric field intensity is high. Where the resultant force is high, the lines of force are so much crowded at that point. So I have already told you that electric charges are concentrated at the tip or at the point where the surface area is small because of charge density principles. The smaller the surface area, the larger the charge density. So the charges are more concentrated at where the surface area is small. It means that the point where all the surface area, the charges are more, you are going to have more electric lines of force there. All right, than a point where the electric lines of force are few. So where the resultant force is greater, the lines of force are more concentrated at that point. These are what we refer to as the characteristics of the electric lines of force. Characteristics of the electric lines of force. So let us use these characteristics of the electric lines of force to draw the lines of force pattern. Now, when we say lines of force pattern, we refer to how the lines of force are arranged for various charges. Exactly. Good. So number 1, lines of force pattern. Number 1, for a point charge. for a point charge. So the lines of force pattern for a point charge, let's take for instance a positive point charge like this. The lines of force pattern around this positive point charge are like this. They are like this. So what that means is that they move away from the positive charge. For a negative charge, they move towards the charge like this. For a negative charge, they move towards the charge like this. So when you pick a negative charge, the lines of force pattern behave like this. So this is how the lines of force pattern behave for a positive charge. This is how they behave for a negative charge. We call them point charges. Good. Number 2. Let's look at the lines of force pattern for two unlike charges. You know, unlike charges will show attraction, right? So for unlike charges showing attraction, showing attraction. For unlike charges showing attraction. So I can have a positive charge and I can have a negative charge like this. A positive charge and a negative charge like this. So between this one and this, they will move like that. They will move like that. And this one will move this way. So this is a positive charge. They will move away from the positive charge. They will move towards the negative charge like this. So this is line of force pattern showing attraction. So these two charges are attracting each other like that. Number 3. So like charges. Like charges showing repulsion. Like charges showing repulsion. Good. So let's suppose that we have two charges like this. A positive, another positive charge. You know, when you draw them, don't put them so much apart, right? Let them be a little bit closer. So the lines of force pattern are like this. So because this is positive, they move away from it like this. They move away from the positive charge. Alright, if they were negative charges, they will come towards it. So what happens is, this represents two like charges that are showing repulsion. We represent two like charges that are showing repulsion. So when this is done, there is a neutral point created between the two charges. The point N, we call it the neutral point. And a neutral point is a region in an electric field or a point in an electric field where the resultant electrostatic force is equal to 0. A point in an electric field where the resultant electric field intensity is equal to 0. That is what we refer to as neutral point. Good. Then we can also have two charged spheres that are placed parallel to each other. Let's suppose that we look at number 4. Charged spheres. Okay, these are not spheres. These are charged conductors. Two charged conductors that are placed side by side. Let's suppose that they are charged positively, like this. The two of them are charged positively. It means that they carry like charges. So the resultant force is going to be like this. And the resultant force are going to be like this. Because they are positive, they will point away to show repulsion. They will point away like this, and they will point away. So if we have two positively charged conductors, two positively charged conductors, this is how the lines of force pattern behave towards them. I can put a lot of them, but you realize that here they will interfere. If I continue, they will interfere like that. All right? Because I don't want them to interfere. That is why. They are not supposed to attract each, they are not supposed to be in contact with each other. Good. So this is how the lines of force pattern between them is going to be like. Then when we have, what that means is that there will be a neutral point here. All right? There will be a neutral point here. Then when we have the same thing, when we have two conductors that are charged, that carry opposite charges. So the top one is positive, the down one is negatively charged. The lines of force pattern between them is going to be like this. All right? The lines of force between them is going to be like this. They move from the positive to the negative to the negative, like this. All right? Good. So that is how they are going to be. I hope you get a concept. So this is how the lines of force pattern behave for point charges, for like charges, for unlike charges, and for charged conductors. All right? Remember that you can be asked to draw any of these. So learn how to draw them and learn how to draw them very well. Thank you very much. We'll look at another term that we call electric field intensity. Now we define electric field intensity at a point in an electric field as the force per unit charge placed at that point in the field. Let me explain this. A charge has created a field. This charge is coming into the field to experience the field. Remember that we are saying force per unit charge. The force between two charges is as a result of the two charges. This charge exerts a force on this charge also exerts a force on this. Please try and get this one. The force between two charges is as a result of the two charges present. This charge exerts a force on this charge also exerts a force on this. So the force between the two charges, which is given by the Coulomb's force as F is equal to K Q1, Q2 all over D squared, the distance between them. We are saying that the field intensity is the force per unit charge placed at that point in the field. So we are supposing that this field has created a field. This charge has come into the field and it is coming to experience the field. All right? So at the end of the day, the force is between the two of them. This one is exerting a force on this, one is exerting a force on this. In order for me to look at the field intensity on this charge, the force that this charge is exerting on this one, I need to take away the effect of this charge from the system. So I need to divide by the quantity of charge for this particular charge. So if I divide the force between the two of them by the quantity of charge for this, then that will give me the field intensity due to this charge on this charge. Let me explain this by diagram on the board. Let's take it that a charge Q has created a field. So this field is for this charge. Another charge, small q, is coming in to experience the field at this point. So we are looking at the field intensity at this point. Remember, there exists a force between the two of them, F. That force F is equal to K, Q, small q, all over D squared, where D is the distance between them, like this. This force is between them. We are looking at the field intensity due to this charge on this, at this point. So what we do is that we have to take away the effect of this charge from the system. So we divide through by Q and we divide through by Q, so that this Q will cancel this Q. And that will give me F over Q is equal to K, Q over D squared. The force per unit charge placed at that point in the electric field is what we refer to as the electric field intensity at a point. Good. So we say that The symbol for electric field intensity is E. And we say that the electric field intensity, E, is defined as the force per unit charge placed at a point in an electric field. Alright, the force per unit charge placed at a point in an electric field. So let us consider the diagram I drew earlier, such that a charge Q has created a field. The distance from here to this point is D. Let small q be the charge that is experiencing the field. The force between them per unit charge placed at that point in the field is not per this charge, but per the charge that is experiencing the field. Alright, that gives us this. The unit for electric field intensity, is given by Newton per Coulomb. So that is the unit for finding electric field intensity at a point in an electric field. So, but the force F is equal to K, capital Q, small q, all over D squared. So when we put this force here, to give us the field intensity, E is equal to K, capital Q, small q, all over D squared, divided by Q. Then Q will cancel Q. That means the field intensity, E, is equal to K, capital Q, over D squared. Take note of these two equations very well, especially this one. This one uses the force and the charge experiencing the field. This field intensity uses the quantity of charge that has created a field and the distance between the two of them. Good. So that brings us to the end of today's lesson. Thank you very much for being part of BJ's Physics Classroom.